Okay, this is just a short podcast on a paper that came from Tim Lee's group. Looks at a bunch of MJOs and clusters them and tries to look at multiple initiation regions. Most of them depend on circumnavigating MJOs. So MJO, let's say, wherever it's born, is going to propagate eastward over into the Pacific, reaches the warm pool, and then get colder temperatures over the cold tongue where convection is not very active because of the cold SSTs, transitions into the Atlantic and comes back over the Indian Ocean. So the suppressed phase or the dry phase of the circumnavigating MJOs have various ways of creating moisture convergence and triggering the MJO initiation from either the MJO that has circumnavigated and back, or being generated primarily or without a preceding MJO. And one type of initiation is favored during La Nina, and another initiation is favored during El Nino, and it has to do with how the upper tropospheric westerlies and lower atmosphere are coupled or decoupled based on whether it's an El Nino or a La Nina. So the essential idea is to do a moisture transport or moisture budget equation. So you're looking at time variability of moisture. Prime here denotes the intra-seasonal time scale. So you take the total moisture and divide it into low frequency, so the seasonal part, which is, let's say, lower frequency than about 80 days or 100 days, depending on which way you pick the time scale. MJO time scale is typically like 20 to 80 days, and then you do a higher frequency which is shorter than 20 days or so, or even 10 days, depending on which bandpass filtering you use. Or you can also do it in terms of wave numbers. When you do typically kinetic energy, people do seasonal cycle wave number 1 to 4 for MJO and greater than 4 for higher frequencies, and so on. So you end up with terms which are basically going to be about intraseasonal winds advecting the mean background moisture, or mean winds advecting the intraseasonal humidities, and so on. In this case, the excuse me, zonal and meridional advection terms are separated from the vertical convergence divergence terms, which become the column processes, column average processes, which are represented as Q bar C in this paper. And this includes also a SST forced part. So as you can imagine, there are times when air-sea interactions are critical for the MJO initiation. Critical for the MJO initiation, and other times it's not so critical. So start by clustering. So clustering result of MJO initiation regions. We are looking at averages over a longitude band, considered Atlantic and Africa, maritime continent, Indian Ocean, and Western Pacific. They are all averaged over 5 south, 5 north. And each region also consider convectively active MJOs and convectively suppressed MJOs. So you can see most of the MJO initiation is happening over the Indian Ocean, with many occurring over the Atlantic and African region, maritime continent, and Western Pacific. The time period used here is 1979 to 80 because MJO straddles the calendar year going from October to April. You start in the fall winter of 79-80 and go through the fall winter of 2018-19. They have done it for November to April, for example. Okay, so starting with that, I'll just briefly show you the processes that are summarized as schematics in these diagrams that we will look at. So we are looking here at the gray band, which is the Africa Atlantic region where the MJO initiation happens, and these particular ones favor typically during La Nina and has to do with the upper level westerlies and lower level winds being more decoupled than during an El Nino. So you have an active active MJO convection over the western Pacific with cold background SSTAs like a La Nina pattern. At day minus 20, associated cold background state also occurs over the tropical Atlantic, and as the MJO moves eastward onto the cold background SSTA at day minus 10, the convection weakens because you are now out of the favorable SST region, and you have the corresponding convergence divergence patterns with strong convective activity here. And by the time you move on to this region, you also are initializing a free upper level Kelvin wave associated with the convection moving, and then you have a suppressed convection here over the western Indian Ocean, which then moves to the eastern Indian Ocean maritime continent by day 0. So this is the circulation that has convection circulation moisture feedback. So associated with this, there is a favorable condition created for triggering convection to its western side due to moisture loading by the moisture advection. So intraseasonal zonal wind anomalies are advecting the gradient of the background moisture minus U prime del x q bar, which is creating convection over the Atlantic and West African region. So this is the main process in the genesis happening over the Atlantic African part between 30 west and 30 east. If we move now to the Indian Ocean, this is the convection genesis of MJOs over the Indian region, which is what happens most of the time, and you can see that maybe these are more associated with the El Nino type of background interannual variability. So day minus 20, you have an MJO that is now in the dry phase, so you have subsidence and suppressed convection, and by day minus 20 the convection has moved eastward, or the suppressed convection MJO phase has moved eastward, and there is convergence at the upper level subsidence, which creates basically acting intraseasonal anomalies on the background westerlies over the Indian Ocean to create air-sea interactions and warm SSTAs, which then are associated also with the suppressed convection, which is feeding it moisture again with the intraseasonal zonal wind anomalies advecting the background moisture gradient. So you have moisture advection, which then triggers the MJO by day 0, which then can propagate eastward. So these strong green arrows imply strong moisture convergence. These red arrows here imply feedback with dry suppressed convection phase of the MJOs. MJO index typically has OLR and wind shear in it, like RMM1, RMM2, the Wheeler-Hendon kind of thing. So precipitation is not always explicitly tracked here, so you have to rely on these indices, which have some implications on how you infer some of these processes. But just the schematic tells you that there are multiple regions of originating or initiating MJOs. The next one is over the maritime continent. This is a schematic diagram of MJO convection initiation over this gray band here, which is straddling the eastern Indian Ocean into the western Pacific, or essentially the maritime continent, which is typically associated with a westward propagating Rossby wave, which again is you can think of it as a circumnavigating MJO, which is creating a process here at intraseasonal timescales. So there is a divergence of winds at the surface, convergence at the top, and you can see that this doesn't have a strong feedback like here, the black arrow, and there is background warm SSTs at in this region in the West Pacific at day minus 16. By day minus 8, you have more of a Rossby wave anticyclone, which is advecting in the moisture into the genesis region over the maritime continent. Here, instead of U prime dx, you have V prime dy q bar term, so it's the meridional advection of the background moisture that's key process in the MJO initiation over the maritime continent, and it propagates eastward, and at day 0 there is very strong MJO initiation with strong moisture convection feedback happening, and the warm background SSTA has somewhat reduced, and now the MJO can move eastward onto the West Pacific. Of course, there is a West Pacific genesis which again relies on the warm background SSTA. Now the gray band is moved over to the east of the maritime continent, again start with the MJO dry phase as opposed to the westward propagating Rossby wave in this case. So you have moisture advection again associated with the anticyclones that are on the western side of the dry phase. And there is again the moisture advection. This time it is the horizontal, so V prime and U prime together advecting the moisture gradients in the X and Y direction. So you have again initiation of convection, and then you have this feedback in terms of air-sea interactions and moisture flux into the MJO genesis, which then can propagate eastward. Obviously, I'm doing it in a very schematic way, using the figures which are provided by the authors, but you can read the details of why there are differences in the genesis processes in each region, and why some processes dominate in one region and others dominate in the other region. But this has to do, of course, with where the convection is in terms of active convection, how the moisture supply is happening, where the circumnavigating suppressed phase is coming over and creating favorable conditions for initiation. So it's a very, very brief introduction, but you should definitely go back and read the paper if you're interested in more details of these processes. So you can think of this as the diversity of MJO initiation and the associated processes, remembering that this paper identifies using the clustering 3 main regions: the Atlantic African region, Indian Ocean region, Maritime Continent region, and the West Pacific region, each of them sending off the eastward propagating MJOs. And El Nino and La Nina affect where the genesis is favored. Obviously they will have consequences in terms of predictions and predictability and impacts on the Indian Ocean, or the feedback to the El Nino itself, and so on, which we will not get into here. Okay.